Yep. All right, so I'll do a quick introduction for myself before I give the word to Lara. I'm a computer scientist from Belgium. Some people may know me from the EasyBuild project. I've been working for over 10 years on EasyBuild. We install scientific software on HPC clusters and beyond that. I like open source software a lot, like I guess most people here. And some people may know me from my How to Make Package Managers Cry talk at FOSDEM. If you haven't seen it yet, you should. Okay, before I give the word to Lara, I'll kick off a VM in AWS, if that works. All right. Let's try it again. I want to use this for the demo in my part of the talk. Ubuntu. If it doesn't work, I have a backup plan. So.
In the meantime, maybe I can already introduce myself. So I'm Lara. I'm a digital art historian, and I got introduced to software packaging early this year in May, when I got hired on the multi-xScale project at the University of Ghent, where I started using EasyBuild and Easy. Me and Kenneth, we work for the supercomputer at the Ghent University. And so what is a supercomputer? The supercomputer that we use is mainly used for scientific computing. And what comes down to what a supercomputer is, it's big, it's fast, and it's expensive. And, and what is mainly done on these computers is scientific simulations, and much, much more. What is also special about these systems is that you have thousands of scientists who work on the same system at the same time, and they also have a very wide background in all different fields, and they use a lot of different software. And for them also, performance is key, because the better their calculations run, the more science that they can do. What is also special is that they use scientific software, which is a different breed. This is mainly because, most scientists are not software engineers, and that's also okay. And so they find things online that they think they can use, and then they try to apply it on the system, and most of the time this will not work. So they need us to help them get it installed so that they can just focus on the science and using that software. And it's also not viable for them in most cases to use standard software packaging tools, because as you can see on the graph, it shows a generic build for GROMEX, and then also an optimized build for GROMEX. And you can see that there is almost a 70% speed up when the software is optimized. So it's it's important that the software is optimized. And so to more easily have this software built from source, we use EasyBuild, which got started in 2009 and is an open source project since 2012. And it mainly automizes the installations from source of now over 3,200 software packages with over 2,000 extensions to that software. And on the graph you can see the growing number of software that we provide installations for over the years. But EasyBuild is no longer enough. So it's no longer enough because the landscape of scientific computing is changing. You have an explosion of software that is being developed in bioinformatics with the AI boom. And so EasyBuild is no longer enough to provide the software that is asked from the scientists. The scientists also ask for more and more different kinds of systems, such as cloud. And you also have an increasing number of processors and microarchitectures, so it's getting harder and harder to keep it up with installing the software on these systems. On the graph, you can see the number of software that is requested at our site, and as you can see, it's growing over the years. We already have now at the moment more installations than what's asked the previous years, excluding 2022. And so the HPC support teams can no longer support this software boom. So all the systems are having the same problem because they're all on an island. And so for each system, they have to start almost from scratch to build this software. There's many different cases on each system. So they run into different problems. Yeah. EasyBuild also, although it automates a lot, it's no longer sufficient to keep up. And a lot of duplicate work is being done. So we suggest a solution with Easy, and that is that those systems can actually just source a software stack from a file system that is available over the whole world. And what we do is we have a compatibility layer that is compatible with all kind of CPUs and also a base OS in Linux. And on top of this compatibility layer, we built the software. So the software is not, does not rely on the base OS and can just run on the compatibility layer. This is an high-level overview of Easy. So we have the file system, for which we use CERN VMFS. For the compatibility layer, we use Gentoo. For the software layer, we use Arch, Pack, EasyBuild, and Almod. And we not only want to provide the software, but we also want to make sure that the software is reliable and that researchers can rely on it. So we also built testing based on reframe so that we can make sure that the software is still good and for the scientists to use. And we have funding for Easy via the multi-xScale project. 50% of the budget goes to Easy, and the other 50% of the budget goes to scientists who will use the software layer for helicopter design, battery applications, ultrasound of non-invasive diagnostics and things like that. And I now want to quickly show you how the user experience with Easy is. So on a system where CERN VMFS is deployed, the user can just source the Easy environment on their laptop and then simply load the modules and use the software. So once the scientist loads the module, a request is sent to a local cache to see if the software has already been loaded on a local cache. If it's there, then the user can use it. If it's not there, it goes to a mirror server and checks and downloads the files from there. And the mirror server is fed by a central server, which makes it easy, provides an on-demand streaming of software like music or TV series.
Yep, okay. A little bit more deep down in each of these layers. So this is an overview of how CERN VMFS works. It's similar to what the previous speaker said. There's as soon as you start using files, they are downloaded on demand if they're not available yet on the system. So that works on an HPC system, that works in the cloud, that works on a laptop. It doesn't really matter. So there's this network of servers that basically provide the installations as you need them. There's a whole lot of details here, but you can check more on the CVMFS website. So this was developed at CERN to distribute the software that they need for their data analysis needs. The compatibility layer, this middle layer, is built with Gentoo prefix. So we build basically a collection of libraries and some small tools, a glibc, a bash, a Python with Gentoo prefix. We do this currently twice, once for x86, once for ARM, 64-bit. And we do this in a rather special location, this /cvmfs, yada yada, so a rather long path, which has a version and which has the CPU architecture embedded in it. This is what we use as a compatibility layer to make sure that the applications in the software layer can run on any Linux operating system. We don't care whether you're running Ubuntu or CentOS or whatever, because our applications basically only use the libraries from that compat layer. In the software layer, we then do the actual real installations we care about, the scientific software, which is again built for different CPU targets, but here for very specific types of CPU. And that way we can optimize, for example, for an Intel Haswell or an Intel Skylake CPU, we provide separate installations which are properly optimized to run on these. That part is done with EasyBuild. We then expose these installations via environment modules, which is a pretty standard system on HPC clusters for which we use LMOD. And with a small library that was actually pulled out of SPAC a couple of years ago, ArchSpec, we do CPU detection, so we figure out what kind of CPU you have, and based on that, we pick the right part of the stack fully automatically. So as a scientist, you don't need to know whether you're running on a supercomputer or a Raspberry Pi, it just all works as you expect it to. All right, I'll show a quick demo of this, and hopefully that VM I've spun up is now actually working. Let's see if that's the case. All I really need is the IP address for this one. I'll copy paste this and then go in here. I'll make this a little bit bigger. And if all goes well, I should be able to log into this VM. So this is basically an empty Ubuntu 22, right? There's a Git here. There's no module command. So I can run module avail like you do with LMOD. Nothing is there. So this doesn't look very useful currently. If you go to the EASY documentation, it tells you how you can get access to EASY. What you basically do is you run these commands, which essentially boils down to you install CVMFS, you install a configuration file for CVMFS, you do an absolute minimal configuration where you basically say I need, or I want to use at most 10 gigabytes of local disk for all the software that you're going to pull in, and that's it. So let's see if we run this in here, what that will do. So that will take a couple of minutes. It's going to download the dependencies of CVMFS itself, install CVMFS, and then it should be working. While it's doing that, as Lara already showed, what we include in our repository is an initialization script. If you source that initialization script, it will do the detection of your CPU, and it will basically update your environment to start using all the software that you care about. For example, R here, we're doing a module load of R. That means we have an R binary available in a very weird and long path, but it is one that's optimized for the CPU that we're running on, which is in this case an Intel Skylake. And you can just start using the software and it all works pretty nicely. All right, it's still installing packages. It's hopefully done pretty soon. It's going to ask me which services I want to enable. I don't really care. Now it's going to do the CVMFS part, the configuration, and that's it. So that means we now have this new location here on our file system. Make it a little bit bigger. It looks empty, but if you actually know what you're looking for, that's the name of the repository. You can start looking what is in there. I'll just source the init script for the latest version we have. This does the CPU detection, so here it knows, oh, we're running on an ARM Graviton 2. I'll update your environment for this, and now you suddenly have a whole bunch of modules available. So that looks pretty cool. To show a quick demo of that, I'll actually run a scientific software package, and I'll let you choose what I need to run, because I don't care, it should all work. So the ones I can support are GROMACS, OpenFOAM, TensorFlow, and Bioconductor. Someone scream? TensorFlow, I was expecting that one. Okay, so what do we do here? We have a small run script. We load a TensorFlow module, which is provided in EASY, and with that TensorFlow installation, we run the Python script, which is also in here in that directory. So let's see what this does. At first, this doesn't seem to be doing much. That's because we're starting to access files which are not available on this client yet. CVMFS will detect that, will download that for us in the background, and when that's all done, it starts running TensorFlow, and it all works nicely. What you're not seeing is that the TensorFlow that is being run here is optimized for an ARM Graviton 2. So it's not just works on ARM, it's also optimized for this specific type of CPU. If you run this again, so this took about 20 seconds, the next time may be a little bit faster because now everything is locally cached and it should be starting significantly faster. And you can do this with any software that is included in the EASY repository. All right, another thing we also do and spend a lot of time and effort on is testing the software. So already on the EasyBuild side, which is the tool that's used to install the software, we run the test suites of the software. So we're not just happy with the binary that seems to be doing something. If a test suite is available, and for projects like TensorFlow or PyTorch, you have tens or even hundreds of thousands of tests you can run, we try to run them, and we try to make sure that test suite fully passes. So we're giving you an installation that's actually validated in some sense. What we're also working on is a portable test suite in Easy, where we want to go beyond the test suite and also run actual examples like I was doing here, and run them over and over again every day, every week, to make sure the software we provide is actually still working, and is also still performing the way we were seeing before. So we're not getting any regressions by changing something or one of the mirror servers acting up or God knows what's going on. So we're going to actively monitor this and do performance monitoring here as well. Another aspect we want to do is we want to make this a community project. So we want, ideally, scientists to be able to add software to Easy, but of course in a secure way. They're not going to send us binaries, and we're not going to include us in the repository. So there's an automated workflow here to build all this stuff from source and get it included. How does that work? A contributor opens a pull request to our software layer repository where they somehow express that they want to add a software package. Right now, this is basically adding a line in the YAML file that says, give me TensorFlow this version with this compiler. Someone looks at this and says, this makes sense. Then they ask a bot to go ahead and do all the builds on each of the CPUs we support. So that's all fully automated in the cloud. Once that is all working, we can even run tests on that and make sure it's working on the build node. But also, we're going to run installations. We're going to run tests for those installations in a totally different operating system. So if it was built on CentOS, we're also going to test it on Ubuntu, and it should work fine because we're using that compat layer in between. If that all checks out, we can upload those installations as tarballs into an S3 bucket, and then eventually they go to that central server, which opens a pull request. So we have here a human, again, making sure that it's OK to actually include those installations in the repository. So that human says, this all looks good. This installation seems to make sense. So they do approve, and it actually gets added to the Easy repository. So we want to make this as easy as we possibly can, as automated as we possibly can, but with all things taken into account, of course. All right, let's see. Good. We have a paper on the whole concept of Easy, how it works, what kind of use cases we envision with this. It's open access. You can go ahead and read it. One thing we did in this paper is look at the scaling of GROMACS across, this is 2 to the power of 7 cores. So I think it was 16,000 cores or something, and in a compute cluster in Germany, in Jülich. And what we did here, we compared the GROMACS that we include in Easy with the one they had on the system. So supposedly the one they have on the system is very optimized for their system, right? The one we have in Easy runs anywhere, and it just does this CPU auto-detection. We were basically getting the same performance as the one that they had on their system. So that shows there's really no serious performance penalty you were getting. You can actually see we're performing a little bit better. That may be because of the newer glibc that we ship in our compat layer, because that has some effect as well. So we may actually be beating them at their own game without knowing much about the system itself. So what is Easy? Easy enables the on-demand streaming of scientific software installations, fully optimized for the CPUs on which you will be using them. It works on basically any Linux distribution. As long as you can install CVMFS on it, you're fine. And thanks to that compat layer, the applications we ship will work anywhere. It's a uniform software stack, so whether you're running on your laptop or on an HPC cluster or in the cloud, you're basically using the same installations everywhere. And for a scientist, that's basically what they want. And we want to make this a community project as well, because the problems we're facing today, the landscape is changing too much. If we don't collaborate more across HPC sites, and even with the scientists and the developers of the scientific software involved, we probably won't make it, so we will have to cut down somewhere, and we don't want to do that. All right, this work is funded by a Euro HPC project, so we're getting money from the European Union, so I have to show this slide. And we're actually also getting help from both AWS and Azure. They're giving us free time in their cloud to do these builds, to do these tests, and to make sure that everything is working fine. We have mirror servers running in there, so it all works really well. And if you want to know more, you can check any of these links or ask any questions you may have.
Okay, and it does look like we have time for Q&A, so if there are any questions in the audience, please feel free to ask them now.
Hi, could you touch a little bit more on the compat layer? Are you doing like the lowest common denominator, like rel 7 or something, or is it working differently?
With Gentoo prefix, we build our own small Linux distribution. I can actually show this a bit more. So if you look into a particular version of EESSI, you'll find 3 directories: the init script, essentially, the compat layer, which is the middle one, and the software layer, which has all the applications. If you look in here, so no, this is just a file system, right? There's no packages that you have to install. It's all there already. The individual files are there already. You can just start straight running this, and it will all be downloaded in the background. We have a Linux subdirectory because we hope we, at some point, can also install support Mac OS, because Gentoo prefix can build Linux, a small Linux distribution on Mac OS. If we have that, we can just build stuff on top of that, and everything should still work. And in here, we have, for ARM, for example, a small Linux distribution with a standard Linux file system bin, user lib. You'll find glibc in here somewhere. Is it here or is it there? I can never remember. It's certainly somewhere. Probably here. Yeah, so this is where you can find glibc. So by shipping this and only linking to this, this is how we make sure that the binaries that we include in the software actually work. If I load R, for example, I don't really care which version. This gives me a binary called R script in this long weird path. And if you run LDD on that, LDD on the full path, of course, without typos, if that's possible, you can see that this is picking up the libc from the compat layer and not from your host OS, which probably also has a libc here somewhere. I don't even know where it is. I don't know Ubuntu, and I don't need to. So that's like the key thing, and that middle layer solves the issue.
It looks like we have one more question over here.
I was thinking, especially when you describe the stacks, it sounds a little bit, like kind of like maintaining a Linux distribution, but obviously not quite. And I guess sorry if this is a strange question. I was wondering. Obviously, it's different in many ways, but since you have this review process, I would just I guess I was going to ask, to what extent do you I guess to what extent do you see it as similar to maintaining a Linux distribution? Now you're doing software packages, which are not the same as a desktop OS, but I'm sorry, this sounds like a silly question, but how much is it like maintaining it? And of course you use Gentoo prefix, so I think that's what landed it. Is it similar to your idea of maintaining a Linux distribution? Or then, this is a silly question, sorry.
So the question is, how close is this to maintaining a distribution? I would guess it's quite similar. It's actually worse, because we're building for all these specific CPUs, right? So what most package managers do is they provide the binary for GROMACS on x86, done, right? And maybe on ARM, 2, maybe Power and RISC-V, that's already 4. Yeah, that's enough, right? You have a lot of software to deal with. That's not sufficient for us. Exactly for the reason that Lara showed, if you run a single binary on your system, you're in the red part of the graph. And higher is better here. So we don't want to be in the red part of the graph. We're running on these hugely expensive systems. We want to use that hardware properly, right? And run it to the extent that it can do stuff well. So all these fancy instructions, AVX 512, we want to use those because that matters a lot for scientific software. Yeah.
And we have time for one more.
So to that, I mean, you are using binaries effectively within EESSI, though, that are compiled on a different system from the one you're running on, right? And so in that sense, like, if you had optimized binaries, you would be okay with that. I mean, because that's effectively what you're doing, right?
So we are running binaries. Yeah, we're providing the binaries in the file system. I don't understand the question.
No, it's the earlier slide said we have to build from source. And so like the EESSI effectively isn't building from source on the machines of the consumers, right? And so it's, right, you are distributing binaries.
We are distributing binaries, yes, but we have to build from source so we can optimize for specific CPUs. Like,
Sure.
where else are we going to get those binaries? You have to build them themselves.
No, for sure.
ourselves.
Yeah, so you need optimized binaries is really the argument,
Yeah.
not have to build from source.
Yes, that's true. We could, if someone gives us optimized binaries, we could use them. Yes.
Yeah.
If they link to our compat layer.
But I mean,
Yeah.
Sure.
So there's.
You guys are providing the optimized binary.
Yes.
Yeah,
Yeah.
but the consumers are not building from source, so that's,
Yeah, indeed. So the consumers, as long as they're happy with what we provide, don't need to build from source themselves. What they can do is they can use our stack for all their dependencies and only build the stuff that they care about on top of that. Maybe GROMACs with different features or God knows what. So that's stuff we're going to enable as well. Yeah. And this is something I always say, and I've been working on EasyBuild for 10 years. It maybe sounds weird, but this is in no way specific to EasyBuild. If there is another tool that can install stuff from source for HPC, we could use that here as well. I don't know if there is, Todd, but.
Okay, and that is all the time we have. Thank you very much, Kenneth and Lara.